Assalamualaikum warahmatullahi wabarakatuh. So our group will present about experimental CO2 capture using absorption hydration hybrid methods. So before we start presenting, I want to introduce myself. My name is Muhammad Hilman Danish bin Muhammad Hamidi, and my group name and my group member was Muhammad Nur Afa Usma, Muhammad Farhanuddin, Nur Atira Kamila, and Muhammad Aminul. So let's start our presentation. So first of all, I will explain to you overview of our article. So the main idea is to investigate a new method to capture CO2 using a hybrid of adsorption and gas hydrate formula. And the objective to test if the hybrid can improve CO2 separation from simulated flue gas. So we approach by using a lab scale experiment with CO2 and N2 mixture, measuring hydrate yield purity, and capture efficiency. And the findings was the hybrid method outperformed conventional absorption with better CO2 purity and yield. So that's all from me. I will pass to my group members.
Assalamualaikum. Hi, my name is Nur Atira Kamila binti Muhammad and my student ID is 2201161. So as for my part is critique point. So critique point number 1 is experimental design and methodology. Strengths. The study was systematically designed with a tight control over key variables such as temperature, pressure, and solution concentration, which are essential for gas hydrate formation. The researchers used a stepwise approach combining adsorption first to enrich carbon dioxide concentration followed by hydrate formation, showing a clear understanding of both mechanisms. This approach demonstrates a solid foundation in thermodynamics and mass transfer, making the study scientifically credible and well-grounded in its experimental logic. Next, weaknesses. The biggest limitation is the use of stimulated flue gas containing only CO2 and N2. In real industry settings, flue gas contains impurities like SOx, NOx, and particulates, which can interfere with both hydrate stability and absorbent performance. Without testing these real-world conditions, the results lack external validity, meaning they might not perform the same way in an actual industrial plant. Moreover, the research was limited to small-scale, short-term experiments. There was no mention for pilot, scale testing, or long-term operation, which are crucial to evaluate system durability and scalability. As a result, while the concept is strong in theory, its practical application remains uncertain. Critique part 2. Data analysis and interpretation. Strengths. The paper provides a clear presentation of experimental data, including trends in carbon dioxide purity, capture efficiency, and hydrate yield under different operating conditions. The figures and tables are easy to follow, helping readers understand how variables like pressure, concentration affect the process outcome. The data supports the author's hypothesis that the hybrid method is more effective than absorption alone, especially under optimized conditions. Meanwhile, the weaknesses. A major weakness is the lack of a statistical analysis. There will be no standard deviation, error margins, or confidence intervals, which make it hard to judge the reliability and repeatability of the results. The study does not specify whether experiments were replicated, so it's unclear whether the observed outcomes are consistent or just isolated findings. Importantly, there was no energy balance or cost-benefit analysis, which are critical when assessing the economic and environmental feasibility of a new carbon dioxide capture method. This lack of quantitative validation makes it difficult to assess whether the method will be sustainable or cost-effective at an industrial level. Lastly, my critique point 3, novelty and practical significance. Strengths. The integration of an adsorption and gas hydrate formation is an innovative approach in the field of carbon capture. While both methods are known separately, their combination introduces a new pathway of improving carbon dioxide and separation efficiency. The approach has the potential to reduce the limitation of each method. For example, absorption provides a fast gas separation, while hybrid formation enables high purity capture. The study contributes new insight to the academic discussion on a multi-step carbon dioxide capture systems, which may be relevant for further hybrid technologies. As for weaknesses, despite its novelty, the hybrid formation process is energy intensive, requiring low temperatures and high pressure conditions that are expensive to maintain in industrial settings. The authors do not discuss regeneration of the adsorbent material, which is a critical issue in cyclic approaches. Without regeneration, the process could become wasteful and economically unviable. Also missing is a life cycle assessment (LCA) or environmental impact evaluation, which are essential to determine whether the method is truly sustainable over time. So, while the study is scientifically valuable, its practical significance is limited until these challenges are addressed through further research and process optimization.
In this project, we used AI tools to support our critique, and it was helpful in several ways. First, AI helped us structure the critique clearly. It guided us in organizing the report into logical sections like the background, research, methods, key critiques, and final conclusions, so the flow was easy to follow. Second, it supported our understanding of technical details. Some concepts in the article, such as energy balance and gas hydrate formation, were quite complex. AI explained this in simpler terms, which helped us understand the process better and identify important gaps in the study. Third, AI actually enhanced our critical thinking. Instead of just giving answers, it encouraged us to ask more questions like whether the method could work on industrial scale or what limitations were missing from the analysis. This helped us go beyond surface level reading. Lastly, it was very useful for writing and editing. It helped us improve the language in our report, making it more formal, precise, and suitable for an academic critique. Overall, AI was a helpful tool that supported our thinking, but the final ideas and conclusion were still our own.
Okay, so for the key takeaways, carbon capture technology is still an exciting step forward as researchers have developed a hybrid method that combines adsorption and gas hydrate formation to capture CO2 more effectively than traditional approaches. These results show higher purity and yield, making this a promising innovation in the fight against emissions. However, there's an important caveat: the experiments used simulated flue gas in controlled lab conditions. Real-world industrial emission contains contaminants like sulfur and nitrogen oxides, which could disrupt the process. This means the method's effectiveness in actual power plant or factories remains unproven. Critical questions also remain unanswered. The study didn't address energy consumption, long-term cost, or scalability, key factors in determining whether this technology is viable for large-scale use. Without this data, it is too early to call it a solution. So, where does this leave us? The hybrid method is an improvised proof of concept and a step in right direction. But before it can make a real-world impact, further testing, especially with real flue gas and pilot-scale trial, is essential. For now, it's promising development but not a complete answer to carbon capture challenges.
So now let's move on, and now we're gonna talk about some recommendations and next steps. So firstly, we need to test this with real flue gas. The thing is, actual flue isn't pure at all. It has stuff like NOx and SOx that could mess with hydrate stability and how well the absorbent works. So we can just rely on lab prepared gas. So next, we've got to look at energy use and cost. Hydrate formation takes a lot of energy, but right now we don't have a clear picture of the energy balance or the cost per ton CO2 captured. Without that, it's hard to know if this is really practical. And lastly, lab tests are a good start, but they are not enough. We need pilot testing to see how this works in the run and under real world conditions. And finally, to sum up, moving forward will require testing with flue gas, detailed energy, cost assessment, and pilot scale trials to ensure scalability. By addressing these steps, we'll be better positioned to understand the true potential of this approach and determine whether it can be a viable solution for large scale of CO2 capture. I think that's all for our presentation, and thank you for your attention. That's all. Thank you and bye bye.